Hello, all. My name is Morgan Grogan, and I'm going to be telling you about my research project that I'm doing under Dr. Alice Walker of the chemistry department here at Wayne State. My research project is titled LoA, which stands for the Librarian of Alexandria, and it's a currently in development tool for finding and obtaining large amounts of data from research papers for the development of further prediction technology. And I just want to say I apologize if my voice is a bit raspy. I'm just getting over a cold. But here, let's get into it.
Okay, so some background info on why I chose this as my research. First off, the scale of research papers in existence is astounding. While it is hard to estimate how many there are likely more than 100 million in existence today, at least. And while I'd love to be able to read all of those myself, it's just not feasible. Scraping preprint servers is as well an established technology. It functions basically the same as a search engine, but then downloads the PDFs automatically for you. Once you have those papers amassed, AI models are a very suitable method for automatically pulling information from those papers, with Megatron BERT style models being the most widely used for domain specific information retrieval. That being said, there are many kinds of AI models, all with pros and cons, so as development continues, I'll be adding support for more types. By combining research paper scraping and AI powered information retrieval, we can enable the ability to create huge data sets of information that would otherwise be sparsely available. And once we have those tables, we can use them to train new AI and infer relationships in the data that would otherwise be very hard to see. Specifically, in my research group, the ultimate goal is to use this to download as much data on the fluorescence of chromophores as possible so that we can easily predict such molecular properties and even set the values of the properties in advance and predict a molecular structure that would give us the desired properties. This will have a huge impact on developing medical screening technology, ultimately saving many lives by eliminating the need for toxic indicators such as radioactive materials and increasing the accuracy of these tests. So what you're looking at here is the main screen you'll interact with when running LoA in interactive mode. It will prompt you to choose an option, either install dependencies, scrape papers, or run inference. We're going to choose scrape papers by pressing 2 and then enter, and then it will prompt us if we'd like to update the metadata of the websites we're scraping. Basically, the first time you run this, or when you want to update for newer papers, it will download all of the tags, authors, and title information of every paper available on these websites. It can take a while, so I'm going to skip ahead here. After it's finished downloading the metadata for the websites, it will ask the user to supply some search terms. For this example, I put in chromophore and quantum yield, but they could be anything. It will then go through and pull out the DOI information of every matching article and save the matching DOI numbers for downloading later. Next, we'll do a Google Scholar search. This works basically the same way, except it takes a full Google search instead of just tags. So here I'm going to select yes to perform the search, then type in measurements of the quantum yield of chromophores. And once I hit enter, you can see it start chugging along, downloading the papers it can as it goes through the search results. Next up, it takes the accumulated DOI numbers from the earlier search and asks if we'd like to try to download as many as we can normally. This means any papers that are publicly available to download, and you can see it start going here as well, this time with a progress bar. After it's done trying to get any it can normally, it prompts the user if they would like to use Sci-Hub to fill in the gaps. In my tests, I've seen that this could potentially magnify the search results by quite a lot, though given the nature of Sci-Hub, I'd like to disclaim that it is very important to exercise caution when using it. If you were to accidentally or intentionally leak any non-publicly available papers, you could face legal trouble because of copyright laws. However, if you're only using the papers obtained for yourself, you should be fine. Once the user has downloaded all the papers as PDFs, the program has to go through and reformat all of them to make sure the PDF encoding is set up properly for the next step. Sometimes HTML artifacts crop up in PDFs and other such issues, so it's wise to let the program do this. Here I'm showing you the website huggingface.co, a repository for trained AI models that are publicly available. In my case, I'm using Gatortron OG, which, despite its name, is a very sophisticated information extraction model that should suit our purposes here. So we grab the end of the URL, and we're ready to run inference. So back at the home screen of the program, I'm going to choose 3 for run inference, then I'm going to choose D for download model, and paste in the link I just obtained from huggingface.co. It will then download the model and store it for use. Here, I just wanted to show what it looks like when you use an existing model. You can see it shows a list of the ones you have and asks you to select one. We'll choose the only one, the one I just downloaded in the last slide. Then, finally, we're going to extract info from these papers. The program will prompt us to input questions that the model will then try to answer using the text of each paper. A cool feature I've already added is that if you type in bracket answer bracket in your question, it will insert the answer to the previous question into your current question. This is useful when you're not sure of the specific topic of a research paper, like the name of the chemical being studied. You can see now that it is running. The output is slowly coming through. There is a max length of the text that can be fed to any AI model, so I've set up the program to break apart long papers into chunks that the model can handle. And we'll go through all the chunks, then the offset chunks, to make sure we didn't clip the answer between 2 chunks. You can see as it runs, it outputs the best answer it could find in the current chunk, which is usually nonsense, admittedly, and a score of how confident it is about that answer. At the end of all the chunks for a given paper, it compares these confidence values and outputs only the answer it is most confident about, thereby negating all the nonsense answers that it found. Okay, so as you can probably tell, that all takes quite a long time to run. So what I've done is gone ahead and made my own file format for an automation script that the program will read and run based on when the auto tag is added to the calling of the Python script. Here I'm explaining how the file structure works and why I've set it up the way I have, but in the next slide I can just show you the file structure here. So here we can see an example script that does everything I just walked you through, but in a way that can be batched on the Wayne State University grid instead of being run interactively. It goes through and performs each task with the given values until it finds the hashtag end at the bottom of the file and shuts down. Alright, let's talk planned features. One of the easier things I plan to add is the option to specify an expected answer type. That way, for example, if you're expecting a number as output, the model could know that it is wrong if it gets a string, and either try again or deem the paper as not containing the desired information. As well, given a numerical answer as a result, I'd like to add in a feature that could iterate over all relevant answers if there are multiple. Basically, you could ask how many chromophores are mentioned in this paper, and then have it go through and ask the same question for each of those chromophores. I'd also like to make my code a bit more functionalized, so each function of the program is accessible without having to run through the whole process again, and I'd also love to add support for more types of models. The most interesting to me as of right now is the long-former model type, as models of that type can handle much more text at once, which would potentially speed things up. Some more planned features. A data cleanup screen is needed, as right now, unless you understand how the code itself works and the file structure associated with it, going through the file system and manually deleting things is going to be a headache. As well, obviously, more preprint servers is going to be a good thing. For the ones I haven't used already, generally they don't want you scraping them without permission, so I'd like to add in a way to specify credentials for doing so. And my last point here is optical character recognition for papers containing images. Not only is a lot of data found in the tables and images of papers, but also some older papers are entirely images just because of the technological limitations of the time. So OCR would enable us to access those. Some current issues and limitations of the program include the Scholar search function kicking the user off after a while when a CAPTCHA appears. This is likely to be fixed by adding in credentials and contacting Google Scholar to see if they'll let us scrape their servers officially. Some of the PDFs end up with improper formatting, and so there's this long process of making sure they're fixed before converting them to plain text, which is itself a lengthy process. I'd like to go in and modify the scraping code to potentially bypass the downloading of PDFs entirely and going straight from website to plain text that we can feed to the AI. As well, currently, my program roughly requires about 500 gigabytes of RAM to run properly. This is because of the chunking system required to process such long papers. This will be driven down by adding in support for more models and memory cleanup functions. It also only currently works on Linux, but that is an easy fix and quite irrelevant currently because of the RAM requirements to run. Once the RAM is driven down, I could easily port it over to Windows and OS X. Okay, that's all I have for now. I want to say thank you to Dr. Alice Walker for suggesting this as research and supporting me as I learn. As well, I'd like to thank Dr. Mark Hicks for assisting me as I learn Python. This is my first big coding project, and I know that I couldn't have done it alone. As well, thanks to anyone who finds this work interesting and will potentially use my program in the future, or even just provide feedback and suggestions. And feel free to check out my project on GitHub, and as well email me if you have any questions. The documentation is pretty sparse as of right now, so don't hesitate to contact me if you have any issues when trying to use it. Thanks again.